questions about homework or anything that I went over last time? If not, then I will continue with today's lecture. Share this. Okay, so today I want to talk about the first algorithmic technique, design technique that we're going to be talking about in this class. The very basic algorithmic technique that we're going to learn is something called brute force and exhaustive search. Again, brute force is something that is different from what you have been thinking about traditionally in the past. So today's plan, my plans today is to talk about a more appropriate definitions of brute force in this context, and then I'm gonna talk about some examples that use brute force, and then I'm going to have some in-class exercises that you guys can think about in class. So brute force is as I said before, is a algorithmic design strategies where you can think about this is the idea where you can use it to design an algorithm for solving a particular algorithmic problems. As we said last time, algorithmic problems has an input and an output. So basically every time when you try to solve a problem, you have some input and output. And the question here is, given the input, how do I generate appropriate solutions that output something using the input that I have? If you look at the definition provided in the book, this is a basic, the most straightforward technique to solve a problem. I think you have done this before in the past, and today I want to highlight it a little bit more so that you get the general sense of what this idea is. And again, there's some terminology here. The force is not like intellectual. It's more like using computer resources to tackle this type of problem. And then there's a just do it approach where the book was saying that this is a description, a basic description. Again, a lot of these you might not know it now, but we're gonna have a better idea once we went over some of the examples later on at the end of the class. So this is a important design technique that we use quite often. I use it in some of my research. This is very basic strategies for solving a wide variety of problems, and you have seen it before. For instance, for sorting, multiplying, matrix, string matching, they gave us a pretty reasonable algorithms. The algorithm typically runs in binomial times for those applications that we're going to be looking at today. Some other time it might take exponential time, which is a topic in the later of the classes. I think it's a few lectures away. And a lot of time it's useful for solving small instance size of the problems. When I talk about small instance size here, I'm talking about where the representation is typically small. For instance, if you're thinking about the number of numbers that you have in order to do your computations, then the number is kind of small, like n to the n squared. You can think about it like maybe 100, 1,000, 10,000, but something about like a million or something that larger, then it might be. It might not be feasible. You will see some of that later on. Why some of these algorithms are not feasible. Okay, so let's go to the example that we have today. So the first example that I have is a very basic problem where suppose that I have a number, right, and I want to raise that number to some n, right, where n is a natural integer. So for instance, I want there's only one marker left. Oh no, it's right there. Okay, somebody put it in the board. Okay. So imagine that you have a equal to say 5, and n is equal to say I don't know like 10, right? And the question here is, I want to compute a to the 10 or a to the n, which is 5 to the 10. Right? So what is the most basic way of computing this?
Multiplying a by itself 10 times.
Yeah, so the most brute force way to do it, just do it straightforwardly. Right? So you will multiply this 5 times. So you would expand this out. So you have a to the n, or in this case, would be 5 to the 10. Right? So you have 5 times 5 times. So it's not hard for this example. Right? And in particular, this is a more general way of doing it. So let's look at a more complicated example. I'm sure most of you already seen this like 100 of times. I would say 100, tens of, right? So what is this problem? Well, if I gave you a list of n items that are comparable, like for instance number of characters, I want you to arrange them so that they are in non-increasing order. This is a typical problem where you have an input array and you want to sort them in a non-decreasing order. And the question here is, what is the most straightforward way to do this? Yeah.
So like one way that would be terrible, but is maybe the most straightforward, is you make a list of all possible lists, and then you check each one to see if it satisfies the condition of being in non-decreasing order, and I'm picking one that is.
Oh, okay. This is called like permutation sort, right?
Oh, I don't know.
So I remember there's like a guy who was telling me that. So when I took 310 or algorithms when I was an undergrad, a few years or a long time ago, like 10 years ago maybe. There's a professor who was saying that there's a line, what you can call a sorting function single time in one line in Pascal or other language, I forgot, or Fortran. And basically, the sorting method is basically permutation. So you permute every single permutation of the array, and then you check which one is in a non-increasing order. I mean, it's very nice, right? It's just one line, but it's not very efficient. Okay, this seems to be very straightforward. What is a more efficient or straightforward way to do this? Yeah.
Find the minimum in the array, put it at 0, and then move the 1, find the next minimum to that 1.
Yes, exactly. Yeah, so that's one way, right? So it's good. So basically, we have an array, and then we want to find the smallest one first, and then the second smallest one, and then third smallest one. We're gonna see that example a little bit more later on. What's another idea?
You could do like bubble sort, where you could like compare two values next to each other and then swap them, and so that they're non-decreasing order, and then you do that however many times you have to until the entire list is sorted.
Yeah, so that basically is another strategy where you look at the largest elements first. Right? You want to make sure that the largest elements is at the end of the list first. Right? And then you keep doing it until you have everything. Right? So the first idea and the second idea are somewhat similar. Right? The first idea is about finding the smallest elements first sequentially, and the second one is about how do you ensure the largest elements always at the end first. Right? And then you keep doing it until you have an order. So most of you probably already know this. The first part is called selection sort, and the second part is called bubble sort. So today we're gonna talk about these a bit more. Just give you a bit more intuition about why they look like this brute force, or I just gave you more detail about these algorithms. Okay, so For those of you that remember what selection sort is, or for those who don't remember, do you guys remember, or depends whether you guys remember or not, but do you guys remember what they are, or what this selection sort is? So if I gave you like an array, can you see the number? Is it, I think it might be a little bit too small to see. Maybe I will try to make it a little larger. Is it hard to read here? Okay. So the general idea of selection sort, as one person said on the back, I should really know your name, but I haven't seen you guys until now. Maybe every time we answer a question, maybe you can tell me your name so that I can get to know you a bit more. So what's your name?
Oh, I'm Andrew.
Andrew, yeah. Andrew was saying that an idea that you were talking about is selection sort, right? So the idea here is what? Well, you for the first array, for the first entry of the array, you want to find the smallest elements. So for this entry, you want to look at the smallest elements from the remaining array, and you want to swap with the first element. So in this case, is 3 here. Okay, so we're gonna swap this with 9. Now, after we swap this, then we're gonna look at the next elements. So what's the next smallest elements? Well, in this case, 19. Oh, this array. Now we're gonna, well, no, it's so we swap this, and then now we're gonna look at the second smallest element. And the second smallest elements will be 1, 2, right? So we're gonna swap 5 with 62. So I just want to show you that this is what happened at the end. Right? So the idea is that for each of the entry, you're gonna look at the smallest elements, and then you're gonna keep doing it until you reach the end of the array. And then through this process, the element is guaranteed to be, or the array is guaranteed to be sorted. So this is the pseudocode of the algorithms. So I think we've seen this in the previous class, but let me just go over them a bit in a bit more detail. So here, this function, selection sort, is going to take in an array of size n, indexed from 0 to n minus 1. Right. Given this array, we are going to store it in a non-decreasing order. Right? So what we're going to do here? Well, the first of the loops is where we're going to try to swap. Right? Here, basically denote the positions where you're gonna swap the element with, right? Or where do you want to identify this the ith smallest elements in the array. So initially we're gonna say the minimum is gonna be at that particular location I, right? And then we're gonna look at every element from j to I plus 1, all the way to the end of the list of the array. And if the element is smaller than the initial elements, I'm going to set the minimum elements to be j, right? The one that we've seen so far. And at the end, we're going to see the smallest elements, right, of that particular index, and then we're going to swap it with the initial elements of I. Are we clear? Yeah, it's kind of hard to see your expression because I can only see your eyes. So I was trying to look at you and see if there's anything unclear or clear. Anyhow. So this is the basic intuition. So here at the I locations, everything before I is going to be sorted, and everything after I might not be sorted. This is the general intuition. Any questions? This is an examples of the book. I was gonna ask you to try to work on it to see what it looks like at the end. maybe we can take some time to think about what the solution will be, and maybe even try to trace to see what it looks like. Do we have line here? Maybe just do a couple of them, like I equals to 1, 2, after I, well, after I equals to 0. Let's just see. Any volunteer? See what, say, after, yeah, go.
17 grade 9 swap.
17 and then, okay, and then where 89 is going to be.
Or 17.
I think everything's gonna stay here. Okay. I go to 1.
I'm gonna solve 29 with 45.
Yes. What's your name again? I forgot to. That was
Sujal.
Sujiro. Okay.
I'm Ryan.
Right. Okay. So we have 2 Ryans in the class. Or, right? You're Ryan.
No, I'm Andrew.
Anthony, I'm sorry, I'm very bad at names. Actually, I remember, so I attended a Harvard Business School class one time, because there's a lot of students in the class. What they end up doing is that they break their own name tag. So every time the student comes into class, they have their own name plate or something that make a little paper, like a triangular shape, and they put their name in front, so that when the professor calls on a particular person, they can know their name. Hopefully we don't have to do that in the class. But I do have a virtual memory though, so I know where you end up sitting. So that's something that I will do. So this is 17, so we say we're gonna swap 29 and 45. And then 68, 9, 30. So are we good? There's also something I copy and paste here. You can take a look. afterward, and then so good. So the next question, as I said, we're gonna try to understand the time complexity of the algorithm that we design. So the next important questions that we're gonna ask is what is the time complexity of this algorithm? So what is the most basic? What is the first question you ask when you look at algorithms and try to determine its running time?
What is the most basic operation?
Uh-huh. What's the name?
Chase.
Chase. Okay. Good. So what is the most basic operation here?
It's the comparison.
Right. Exactly. Right. It's the comparison. How many times are we doing the comparison? I guess we already know the input size anyway. Like it's order n, right? The number of elements of the array. So this is the number comparison. How many times are we doing the comparison? We just set up like a like a function, right? Which is
n minus 1 times n minus 2 times.
Yes. Well, so let me write up and just to explain your reason. So this is from I equal to 0 to n minus 2, and this one j equal to I plus 1 to n minus 1. This is 1 because we're doing this is a 1 here. We're trying to highlight because we're only doing one comparison inside. And then we're gonna try to solve this. If you recall, we solved this last class. I'm not gonna try to resolve it here, but the complexity is like n. Do you remember? It's like n times n minus 1 over 2, roughly. And there's big O n. Because you can substitute, so you can use the formula to compare this. I think we did this last class. You can take a look. Again, this is the sum that I kind of rolled out in the class last time. Okay, good. Any questions about this? Okay. Now that we're pretty clear about selection and sort, let us move on to understanding bubble sort. So here's what bubble sort looks like. I'm going to try to go over it just to refresh your memory, and then I'm going to go over some examples about this. So what is the general idea here? As people getting
Tom.
Tom. Oh, I never asked anyone. That means that I cannot forget if I haven't
That'll
asked.
do it.
Tom. Okay. Okay. So here, what is bubble sort? So here, bubble sorts again takes an input of an array of size n, and you want to do some operation to this array so that you have a number that sorted in non-decreasing order. So what is happening here? Well, so here the algorithm is n minus 2, and then from j equal to 0 to n minus 2 to the minus I. And then what's going to happen is that it's going to compare pairwisely, and it's going to swap aj and aj plus 1. If aj is larger than this aj plus 1. So it's going to pairwisely swap the elements and percolate up all the way to the end. So what you're going to see at the end here is that everything at the end gonna be sorted, and everything from the beginning it might not be sorted. So this is the diagram. When you have I at this location, then everything from n minus I all the way up to n minus 1 is gonna be sorted, and everything before that is not gonna be sorted. Oh, we don't know it's gonna be sorted. It might not be. It might already be sorted. We don't know. So let's go over some examples. Here's example. I was gonna have some animation here, but somehow it didn't show up. But anyway, so we have an array here, right, from 33, 37, all the way up to 18. Right? So what is gonna happen here is that it's gonna start from I equal to 0. Right? It's gonna pairwise compare this. Right? And basically what's gonna happen is that if this is if this guy is larger than this one, it's gonna swap. Right? In this case, it's not the case, so it's not gonna swap. Now it's gonna move on to the next one, and it's gonna ask the questions of, okay, are we gonna swap? Right? Well, in this case, it's not gonna swap because 37 is smaller than or 95. Now we're gonna move on to the next one. This one's gonna swap because we know that 12 is smaller than 95, so we're gonna try to push 95 up. So we're gonna keep doing this pairwise comparison until we reach the end, and at the end we're gonna have the largest number, 98, when we do the pairwise swapping. And after this iteration, the first iteration of I, we're gonna guarantee that this 98 or whatever is at the end that we have gonna be sorted, right? N minus I, everything after n minus I gonna be sorted. Are we good? So let's work on a example. I think this is the same one that we have here. Let me erase this. I just want to see what it looks like after. Should we try this one? So what would this look? Yeah. So when I equal to 0, j equal to 0, what's gonna happen? Equal this part here. So you have A of 1, let's say go to A of 0, you're gonna swap. This is the case. What's gonna happen here to this guy? You're gonna swap this. So we're gonna have what we're gonna have? What are you gonna have?
45 swap.
Huh?
89 and 45 swap.
Then we're gonna have 45, 89, right? And everything else gonna stay the same, right? Because we don't do anything. And then when j equals to 1, then what's gonna happen? Because yeah. So we just, and then this is equal to 0, and then when j equals to 1, then what's gonna happen? Yeah.
89 and 68 swap.
This one, and then 45, 68, 39, now, j equals to 2. And you don't really do anything because it's here. Are we good with the idea? Again, I just in case I put some there for those of you that want to look at it after class. So good. So what's the next question we should be asking? Is the time complexity questions. So what's the time complexity here in this case?
Yeah. The basic operation is the inner comparison and the inner for loop. So it'll be two summations, one from 0 to n minus 2, and the other one for in the inner summation from 0 to n minus 2 minus 1.
Example. Okay. 0 to n minus 2 j 2. Again, this is similar to what we saw earlier, and we can solve this. Are we okay with this differentiation? Good. Okay. Okay, great. So we're good with sorting. So these are two algorithms that we're going to be talking about. Later on, we're going to talk about our sorting algorithm using a different types of algorithmic idea. But these are the one that the two that I talked about use the idea of proof first. Now, the next questions, I think most of you are kind of familiar with, is the searching problems. Here in this searching problems, we're giving a list of n items, and we want to check if there is an items that have at least or a value of k, exact value of k. And I was going to ask you what's the most straightforward way of doing it. I thought this one's going to come out differently, but it came out. and so the basic idea, you check one by one, right? And then you find the k elements. So that's the most preferred way of doing it. Do you guys know what this called? I think there's a terminology for this.
Needle in the haystack.
Needle in the haystack.
That's what they call it.
Check each one of them at time. Okay. That's true. Needle and paper. I like that too. But they also call us a question. It's like we saw it a few times before. Again, this is an algorithm. I don't want to go over this too much because we already seen it many times. But the important thing here is that what is the time complexity here? I think this one is a bit tricky because there's like a while loop here, right? And then we want to really thinking about what is the worst case operation this algorithm is going to perform. My mouse gets dry. What would be the time complexity of this algorithm? The worst time complexity.
In the worst case, the last value will be the, because we're starting at 0, so we'll have at n minus 1 will be this k, so will be
Andrew.
Andrew.
Yeah, that's what
Andrew said.
So this is the basic operation, right? The comparison. And essentially what's going to happen is that at the end, we might need to go to all the elements in the array. And either we find it or we don't. If you don't find it, then we might just exhaust the whole array. And the running time is n. So what is the best case running time? Just for fun. I mean, not that we kind of care about too much in this class, but what do you think the best case running time would be?
Just one,
Just one, because
if it was the first element.
yeah, that's the first element that we've done. But anyway, so that's my questions. Okay, so the last examples I have. Hopefully, I still have time. And just usually I don't keep track of time. Okay, I still have 10 minutes, so I'm good. Okay, so the next problem that I want to talk about is string matching. So how many of you heard about string matching? So most of you have already heard about this. So the question here is that suppose that you have a string of n characters, which call text, and then you have n characters, which call pattern, and you want to find a substrings of the text that match the pattern. So this is an example. So here's, I know my name is Al, and then I want to find me in it. So the question is, what is the most straightforward way of doing this? Yep.
I'd say, so you look at the first character in your pattern, and then try to find that in the text, and then check to see if you find an M in this case. Check to see if the letter after it, or the character after it, is an E. And then just keep going like that.
So just what Chase said. And so he was able to figure out an algorithm to do this, right? So the algorithm here, what is this algorithm? Well, so for each of the characters, so you're gonna have to align this pattern with this character, and then you check every single element. If it doesn't work, if it doesn't match, then you slide over one. Then you match every character again, and then you slide over one, and then you keep matching it until you find a pattern or you don't find it. Here's an algorithm in the book gave. Again, it's exactly what I described it. Essentially, what's going to happen is that you have two input. One input of size m minus 1. The other input is what you're trying to match of size m. So one is m and the other is m. And the idea here, as I said, you want to start from the initial positions of the text, and then for each of the positions of the pattern you want to match, you're going to try to compare to see if they match, right? If they're aligned, right? And then if not, then you slide over one, and then you keep matching it until you find a pattern or you don't find one. This is what the algorithm end up doing. I was gonna do an example, but I'm sorry running out of time. But here's a general idea. So I'm just gonna do. And then the first evaluation, this is you're gonna align this here, and then you're gonna try to compare this, right? If the initial character doesn't match, you can slide this over, right? And then you slide over to this slot. Okay. So, but this initial character doesn't work, then you're gonna slide over, and then you're gonna keep sliding over until you hit this part meet. And then what's gonna happen is that M is gonna match together, and then it's gonna check the next one, and then basically the algorithm kind of terminates. If it doesn't, then it's gonna keep matching it until the end, or comparing until the end, and it might not you might not end up getting anything. Are we clear about this? So the question now I would be asking is, what's the time complexity in the worst case possible?
I think it would be like m times n minus m. Because if you have a bigger pattern, then you're gonna go like through it less times.
Mm-hmm.
But if you have a bigger pattern, then you have more things to check each time.
Mm-hmm.
But since it's gonna be like m squared minus like m times n, I think. Oh, actually, yeah, it still depends on both inputs. So, yeah.
Okay, let me Elon, what Elon says.
Yeah.
Correct. It's close to being correct. So you have C of n, right? And then now the C of n is gonna have two sums. The first sum is gonna go from I equal to 0 to n minus 1. N minus m. And the second sum, well, here there should be a second sum, but you can think about it. The worst case is gonna go from j equal to 0 to n. Right? The worst case, you can compare everything in this string. So what's gonna happen is that you have j equal to 0 to n minus 1, and then the comparison is this equality, right? So you're doing comparison. This would be this. And this is relatively easy to solve because we have this n minus 1 minus 0 plus 1, so we have n in the first sum, and this guy is going to give us. So we're going to be n minus n plus 1. But at the end of the day, this would be roughly n times n. Big O of n times.
How do you get like big O of m times n? Because when you distribute the m, you get like an m term and an m squared term. Right? So I guess I'm thinking like, what if the pattern was as long as the string?
Yeah, so if the pattern is as long as the strings, then you have kind of n squared. So suppose that if m is equal to m roughly, then you still have big O n squared.
Oh, yeah.
So this one is kind of more generic, because a lot of the time people can say, oh well, this is also big O of n squared, because if you assume that n is greater than equal to m, then this will still be okay. So here, just a more generic form I'm putting in.
The cost function would also have to take as input m, right? If we were to write this out.
Yeah, you're right. Yeah, so it should also be m as well, but I'm just abusing notation here a little bit. Thanks. Any questions? I think we still have some time left. Here's 2 questions I was gonna ask you to figure it out or to think about. So we still have a couple minutes. So for these questions, I want you to think about what is the most basic way of doing this, the first way of solving these problems. So for the first problem, you have, and so the input is an array, and you want to figure out what is the largest number of times, or the number that appeared the largest number of times. And the second question is what is the kth largest elements in the array.
So for problem 1, would you just count up how many number of times each element occurs and then compare those to find the maximum?
Okay. You guys happy with the answer? Yeah, I'm pretty happy with the answer. This is a long way to do it. What do you think the count complexity would be?
I guess it'd be maybe n squared.
So for instance, I think one way of implementing this is to have like a hash map or have like a table that store the elements in the array. And then basically that we can do order n, so you scan everyone and find all the unique elements. And then the second thing is for each of the elements inside the array, then you can count. Basically you can sort of have a counter array, and then for each of the elements you're gonna increase it by 1. So that means that you only need to have 2 separate loops from doing it. So I think you can do this in order n. I think there's an n² solution that you can think about. So the n² solution sort of require what you're saying. You have double for loops inside it, and then for each of the for the elements in double for loops, then you count how many times the elements gonna be up here, and then you just record the largest element. I think sometimes I remember some Facebook interview questions or some other questions they ask you, like different way of solving this. Like what they might ask you, okay, what's the quickest way of solving it? One of them you're using like extra space. So the first idea that I had is start to use extra space because you'll have to create like a hash type of function at the beginning of like a counting array. So you use extra space, but you're reducing line time because of that. But on the other hand, you don't want to use extra space. Then I wonder if there's a quicker way to do it. But n² would be one puzzle solution. How about for the second one?
Well, one way you can do it is just sort it, and then count down from, or whatever you know. So that, if you use the quickest sort algorithm, that's like n log n, right? And then the second part is only n, so it would be n log n.
That's one way. Is that good for us?
Kind of, I mean. Oh, or you could use one of the sorting algorithms we used here today, but then it would be n squared, because that's the limiting
Yeah, I remember last year I heard the same answer. Like basically for both the problem, you can also sort it right first, and then when you sort it, then you can kind of scan from left to right with the first questions as well, and then you can just count sequentially. Because when you sort it, then all the repeated elements gonna appear lumped together. So all you need is have a counter to scan from left to right. So instead of avoiding this n squared loop or double loops, nested loops. For the second one, let me just quickly say this. The same idea will work. So you make a counter, or not a counter. So basically, for each of the elements, you can count how many of the numbers are strictly smaller than them. And then if this the number of elements smaller than them is k minus 1, then you know that this element is the k largest element. Does that kind of make sense?
But that's n squared, right?
Yeah, that's n squared. Yeah. That one is take a little bit longer, but that's one way of doing it. Yeah. Do that. So we're good for today. If you have any questions, let me know.